Okay, so today we will start with this topic, differentiable convex function. And right now there are 25 students are connected, so okay, we start with today's class. Okay, so there is a uh, theorem, and that theorem says that so if any function, suppose if we suppose that f is differentiable function, this is differentiable of order 1. Okay, so this is differentiable function on an open set, uh, that is of course convex set. Of course, that set is convex. So if f is differentiable function on an open convex set C, and that C set is obviously, you know that this set is belongs to Rn space. Okay, so then you have to prove that this function f is basically convex function. This function is convex on that domain. So this is on C. If this function satisfies certain condition, okay, and that condition is if and only if condition is if and only if the condition is for any two element of that convex set C. So we say that for each x1 and x2 that belongs to convex set C, you have to prove that this relation, that is fx2 minus of fx1, this is greater or equals to gradient of that function at this point, the second point, this fx2 minus fx1, this transpose, okay, x2 minus x1. If this satisfies this condition, okay, this means if you have a function which is defined on, suppose any space. Okay, so here if we take say any point here, like that point is z, and say here this point is suppose x and this point is suppose y. Okay, and if you know that this function is a convex function. Okay, so you know that this function is convex. Okay, so if we take this point z of this convex function and try to draw the tangent at that point. Okay, so this is your tangent equation. So here the main concern is this. Here the function value of at this point is fz. Okay, and what is the function value at this point is fx, and similarly with that point of this function is fy. Okay, and this function is convex function, and that convex function is f. Okay, so now here what is the equation of this line? This line is basically, this line is fz, the grad plus the slope of this curve at this point is a gradient of fz. Okay, gradient of z, and the distance between what is the value of that? That is y minus z. Okay, so this is the equation of this straight line. If we consider that, okay, and here what is the value of at this point is fy. You see that this fy is always greater than this straight line. Okay, and this straight line equation has fz plus gradient of fz transpose y minus z. Okay, so if this condition holds, this means fy minus fz is always greater or equals to this gradient of that. Okay, similarly for this point you can write for this x minus z point, you can write down the equation of this line as fz, or this from your point plus gradient of this fz transpose, and here is x minus z. This is x minus z. Okay, so this line is always less than the functional value of this fx point. Okay, because this function is your convex function. So here, if you try to see that this fx is always greater than this thing, this means fx minus fz is always greater than gradient of that x minus z. So this means this basically represent this condition. Okay, so you have to prove that this condition. Okay, so now let us start the proof. So here we suppose that your function is convex and your set is convex set. Then we try to find what is the value of fx2 minus fx1. Okay, and if we are able to prove that this fx2 minus fx1 is greater than this value, this means this condition satisfies. And the converse part, if this condition is satisfied when function xc is your convex set and where x1 x2 belongs to that convex set, then you have to prove that this condition, if this condition is satisfied, then you have to prove that that function is your convex function. Okay, so here firstly we have proved that the main assume that this function is convex and then try to prove that this relation, and the converse part we assume that this is true, then f is convex. Okay, so let us start with your function is differentiable and convex. This be differentiable function. Differentiable convex function is defined on set C, and that set C is also convex. And if we take any 2 points, suppose x1 and x2, that belongs to that set C. Okay, and here we take the parameter that is theta, which is lies between 0 and 1. Okay, so if we take this theta, which is lies between 0 and 1, so we have basically, you know that if your function is convex, then this value of f of the convex combination of these 2 points 1 minus theta of x2, this is always less or equals to theta of fx1 plus 1 minus theta of fx2. Okay, so either you can also rewrite this form as theta of fx1 plus 1 minus theta of x2. This is greater or equals to f of theta x1 plus 1 minus theta x2. Okay, so either you can write this thing or we interchange left and right side. Okay, so this means this thing. Okay, so here if we try to solve this two, this becomes okay. So you can rewrite this function as this becomes okay. So either we can take in this form fx2 minus fx1. Okay, so in this sense we have to take in okay. So we change a little bit here, and because for this condition we prove that this fx1 minus fx2 is greater or equals to this x2 transpose. Okay, so here we need some change here, and here we take theta of okay, so we take 1 minus theta of x1 either in this form and plus theta of x2. Okay, so no problem here. Okay, either you take this or this thing. Okay, so this is less or equals to you can write 1 minus theta of fx1 and plus theta of fx2. Okay, so if we take this thing, or you can rewrite this equation as 1 minus theta of fx1 plus theta of fx2. This is greater or equals to f of 1 minus theta x1 plus theta of fx2. Okay, so now if we try to solve this thing, so this becomes fx1. How many is it? Hello? हाँ हाँ बताएं. हाँ 100%. हाँ वही तो बस सही है. ये सब ठीक. वही तो बहुत ज़्यादा जरूरत नहीं है. हाँ दवा बस 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 वही बहुत है. वही बहुत है. और या तो फिर पूछ लेते हैं किसी से. अभी हम थोड़ा क्लास ले रहे हैं ना, तो क्लास ले लेते हैं. हाँ 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 ठीक ठीक. ओके. So fx1 minus
Sir,
हाँ
sir, someone is trying to join the class.
fx1 this if you multiply here fx1, and here if we take theta common, this theta is fx1 fx2 minus fx1, and this theta equals to if we take this x1 minus theta of x1, so this becomes okay, so we can write here x1 plus, if we take theta common, this becomes x2 minus x1. Okay, so because we need here this gradient of theta x1 transpose, that's why we take in this form, we take 1 minus theta here and theta here. If you interchange x1 and x2, means fx1 minus fx2 gradient of fx2 transpose x1 minus x2, then you take here fx1 plus 1 minus theta of x2. Okay, so for that reason we simply change this theta and 1 minus theta here, because you take any 2 points x1 x2 or x2 x1 vice versa. Okay, so now this implies that this becomes if we take this value, so this becomes 1 minus this plus fx2 minus fx1, so this sign becomes plus because fx2 is plus sign. Okay, so this is theta of fx2 minus fx1. Okay, this is greater or equals to f x1 plus theta x2 minus x1 minus of fx1. Okay, because this fx1 is goes to right hand side. Okay, and you know that this expansion of this function about this point x1, so this equals to basically f of x1 if you're using Taylor's expansion here. So this plus theta and first derivative of this fx1 transpose, because this is a vector value function, and this x2 minus x1, and here we say only the first order differential function, so no need to write the higher derivatives. Okay, so here plus additional terms here, of course the Taylor's expansion, and then minus of fx1. Okay, so here this fx1 and this fx1 is cancelled out. Okay, so this fx1 and this fx1 is cancelled out, so you may rewrite this equals to theta of fx2 minus fx1. Okay, and this term is greater or equals to, and here there are some additional term plus additional terms here, and here this function is only the first order derivative term, so other terms are negligible here, and you can take here this is addition of some term, additional term. If we subtract or remove that term, so this term is also smaller than the previous one. So this is also this term is already smaller than this fx2 minus fx1, and if we neglect the other terms, this term is again smaller than this term. Okay, so that's why this equals to theta of fx1 transpose x2 minus x1. Okay, and here we're neglecting that term. So this implies you can here theta, if we cancel out to both sides, you can obtain fx2 minus fx1, this is greater or equals to gradient of this fx1 transpose x2 minus x1. Okay, so here this is the final result. You can see that here fx2 minus fx1 is greater or equals to gradient of this fx1 x2 minus x1. Okay, so if your function f is belongs to C1, means that this is the continuous differentiable first order continuous differentiable function, then any x1 x2 belongs to C, this satisfies this condition. Okay, and the converse part is that if this condition is satisfied, then you have to prove that your function is convex function. Okay, so in next page we take the converse part and suppose this condition is satisfied. So in next page, conversely, suppose that if this condition is satisfied, the condition is fx2 minus fx1, this is greater or equals to gradient of fx1 transpose x2 minus x1. Okay, so if this condition is satisfied for any 2 points which belongs to the convex at C. Okay, so now you know that your set is convex set. So any convex combination of these 2 points, so if we take tau and 1 minus, this is also belongs to your C for any theta which is lies between 0 and 1. Okay, so if we using that this is an arbitrary point which belongs to C. Okay, and for any 2 points that belongs to C, this formula is satisfied. Okay, so now we take, so now we have, if we take fx2 1 point, and the second point is not fx1, we take this point. This point is as a second point, and this point is also belonging to C. So here we take fx2 minus f of this point, which is also belongs to that convex set C. Okay, so we take this point. Okay, and now we apply this formula. So this fx2 minus this x, any x, okay, which belongs to C, this greater or equals to, this is greater or equals to gradient of this point. The gradient of this point is f of this theta x1 plus 1 minus theta of x2 transpose and x2 minus x1. This means x2 minus that point. So x2 minus, and this point is theta of x1 plus 1 minus theta x2. Okay, so you apply this formula for any x, and that x is belonging to C. Okay, so now this can be rewritten as fx2 minus f of theta x1 plus 1 minus theta x2. This is greater or equals to gradient of f at point theta of x1 plus 1 minus theta of x2 transpose, and we try to solve this thing. So this is a this term is we try to solve this is x2 minus, this becomes theta of x1 minus of x2 plus theta of x2. Okay, so here this x2 and x2 are cancelled out, and if we take theta will be the common, so this becomes x2 minus x1. Okay, so this term is theta common, and this is x2 minus x1. So now you can write this value is theta be the any scalar one, so you can write here this is theta. Okay, and here x2 minus x1, because this is a vector quantity, so multiply that, and here theta with the scalar one, so you write this that term here. Okay. Similarly, you can uh, redefine this formula by if we take this arbitrary point x in place of x2 here. Okay, so this means you can write f of this theta of x1 and 1 minus theta x2, this point minus of fx1. Okay, so you can write that form in another way, like we take first point is x1, we take first point is x1, and second point is this theta of x1 plus 1 minus theta of fx2, because we have to find that term. So this is greater or equals to gradient of f, and the minus term is that this gradient of f that at that point, this point is 1 minus theta x2 transpose, and then x2 minus x1. So this means this point is your second point, x2 minus x1. This is x2 minus of x1, that is t of 1 minus theta x2. Okay, this term. And here, if we try to solve that term, so here, if we try to solve, then this term is x1 minus theta x1 minus of x2 plus theta of x2. Okay, so now x1, so we take 1 minus theta of x1, and here if we take minus of x1, okay, and then plus, if we take x2 common, so this becomes minus 1 plus theta. So we take here minus of x2 common, so this becomes 1 minus theta of x2. Okay, so this equals to we have to rearrange x2 minus x1, so that's why we take minus of 1 minus x1 common. So this equals to x2 minus x1. Okay, and this term is scalar one, so here we write here minus of 1 minus theta, and then gradient of f theta x1 plus 1 minus theta x2 transpose x2 minus x1. Okay, so here the right hand side of these two equations, suppose this equation is this equation is A, and suppose this equation is B. Okay, and here what is the this term is fx1 minus theta x1 plus 1 minus theta x2. Okay, this term. So look here, this term is theta of that term, and here this is a minus of 1 theta in this term. If we multiply here 1 minus theta in equation number A, and multiply theta in equation number B, and if we adding these two, okay, so what we get? Okay, so now we multiplying the first equation, so multiplying equation A by 1 minus theta and equation B by theta. Okay, and adding we get, and adding we get. Okay, so if we multiplying here the theta 1 minus theta here, so this becomes 1 minus theta of fx2. Okay, minus 1 minus theta f of theta x1 plus 1 minus theta x2, and here theta, so this theta of fx1 minus theta of x1 plus 1 minus theta x2. So this this is the left hand side. This is greater or equals to, if we multiplying here 1 minus theta and here theta, and we adding this, so this becomes 0. Okay. So now this implies here you take theta of x1, and here plus 1 minus theta of fx2. This is greater or equals to this term, it goes to the right hand side, and here this 1 minus theta, so if you multiply here to minus 1 plus theta, and plus theta and minus theta, this are cancelled out. So here simply minus term. The minus term goes to the right hand side. This is f of theta x1 plus 1 minus theta of fx2. Okay, so you see that this f of theta x1 plus 1 minus theta x2 is less or equals to theta of fx1 plus 1 minus theta of fx2, where this x1 and x2 belongs to convex at C, and the theta belongs to 0, 1. So this implies your function f is convex. Okay, so here the converse part, you can easily prove that this function is converse because this condition holds. Okay, so now you can also prove that there are another theorem which is very similar to this. If any function which is differentiable, and if this satisfies this is strictly greater than, okay, this inequality sign is strictly greater than that term, so that function is your strictly convex function. Okay, so you can prove that theorem by replacing that inequality sign greater or equals to by using simply greater than sign. Okay, so if f is your function is strictly convex, then you are able to prove that this fx2 minus fx1 is strictly greater than that term. Okay, and the converse part, you can take this strictly greater than sign on here, and you solve this sign is you find here this is strictly less than, therefore f is strictly convex function. Okay, so there is a similar proof for the strictly convex function. Okay, so there is no need to solve again by using simple replacing that sign with strictly sign. Okay, so you can do this by your own. Okay, so next theorem, if on next page there is an important theorem. So on next page, so if f is differentiable function, f is a differentiable function on an open convex set, C in Rn, then f is strictly simply हम convex ही लेके चलें, then f is convex, then f is convex if and only if for each x1 and x2 which belongs to convex set C, there is a formula. That formula is gradient of fx2 minus fx1 transpose x2 minus x1 always greater or equals to 0. Okay, so If f is differentiable function on an open convex set C in Rn, then f is convex if and only if for each x1 and x2 belongs to C, then this condition hold. Okay, so this proof is very simple, and you have to only use previous formula, and that formula is so let f be convex on set C, then for any 2 points is x1 and x2 that belongs to C, by previous theorem, okay, by previous theorem you know that this fx2 minus fx1 is greater or equals to gradient of this minus sign, that is fx1 transpose x2 minus x1. Okay, so you know this formula. Okay, but any student you can write this form fx2 minus fx1 in not form, that is you take this manner fx1 minus fx2. Okay, so in that sense this formula is write down gradient of at that point fx2 transpose and here x1 minus x2. So this formula is like this way. Okay, and if we are try to adding these two, okay, so if we adding the above two inequalities, we get this gradient of fx2, okay, fx2, and if we adding here, so okay, so we can write in this manner. Left hand side, if we adding this, these two are cancelled out, so this is become 0, and this is that term is gradient of fx1 transpose x2 minus x1 and plus gradient of fx2 transpose and here x1 minus x2. Okay, so you have to prove that this x2 minus x1. So here this is x2 minus x1, but here this is x2 minus x2. So this vector can be rewritten as in this form: this fx1 transpose. This is x2 minus x1, and here we write in this manner. This vector is x2 minus x1. So that's why we take minus sign here. So now that this vector is x2 minus x1 and this vector is also x2 minus x1. So this becomes a gradient of fx1 transpose minus gradient of fx2 transpose, and this is x2 minus x1. So this is less or equals to 0, but here you have to prove that this is greater or equals to 0. So that's why you can write this fx2 gradient of fx2 minus gradient of fx1. Okay, if we multiply by minus 1 sign, so this becomes this thing, and here x2 minus x1. So this is inequality is changed because if you multiply by minus 1, this is the lesser equal to sign, they change by greater or equal to. And you know that any vector A transpose plus or minus B transpose, that equals to A plus minus B transpose. So that's why you can say here is gradient of fx2 minus gradient of fx1, and that transpose x2 minus x1, and this is greater or equals to 0. Okay, so this is the first part. Okay, this is the first part. You have easily proved that if your function is convex, then this satisfies this condition. Okay, so you can easily prove that this thing. this condition is hold. Okay. Now, if we take this condition holds and we take any 2 point x1 and x2 belongs to C, and we are able to prove that that function is your convex function. The converse part. So in next page we take the converse part. Okay. So conversely, or we prove the converse. So we have to assume that this 2 point x1 and x2 that belongs to convex set C, and since you C be the convex set, so the convex combination of these 2 points is also belonging to that uh, set C. So since C is convex, so theta of x1 1 minus theta of x2, this also belongs to that set C. Okay, for any theta which lies between 0 and 1. Okay, so now by using mean value theorem, so now by the mean value theorem, we have this f of x2 minus f of x1 is equals to gradient of f theta of x1 plus 1 minus theta of x2 transpose x2 minus x1. Okay, so but by assumption, this gradient of f is theta of x1 plus 1 minus theta of x2. If we take here x2 in place of x2, we take any point which belongs to that set C. This minus gradient of fx1, and we take this transpose, this into x2 minus this term, this becomes theta of x1 plus 1 minus theta of x2. This minus x1, this is theta equals to 0, because you have proved that if this condition satisfies, and that condition is fx2 minus fx1 transpose x2 minus x1, this is greater or equals to 0. So here we take this x2 in place of that is you take a convex combination of these 2 points. So that's why we take this point is okay here, and similarly we're putting here. Okay, so now if we try to solve this value, this is a theta of x1 plus x2 minus theta x2 minus x1. So here if we take x2 common, so this becomes 1 minus theta, so 1 minus theta of x2, and here 1 minus theta is x1, so this becomes 1 minus theta x2 minus x1. So that's why this value is equals to 1 minus theta, because this is scalar one, this into gradient of f, this theta x1 plus 1 minus theta x2 minus gradient of fx1, this whole transpose, and this value is 1 minus theta, so this is a scalar one, and into x2 minus x1, this is greater or equals to 0. Okay, now you can take this gradient of f, this theta of x1, 1 minus theta x2 transpose, because this transpose, okay, and here the 1 minus theta is because theta is less than 0 and 1, so this value is always greater than 0, so that's why if we dividing by that term, so this is also greater than 0. Okay, so this minus gradient of fx1 transpose, so x2 minus x1 is greater or equals to 0 due to 1 minus theta is greater than 0. Okay, so here if we take theta equals to 1 here, that equals to 0. So this is greater equals to 0, that's why this is equals to that. So this implies if we take this gradient of theta x1 plus 1 minus theta x2 transpose with that vector x2 minus x1 minus gradient of fx1 transpose x2 minus x1. So we multiply that vector to both terms. So this is greater or equals to 0, or you can write down this gradient of f of theta x1 plus 1 minus theta this transpose x2 minus x1. This term is greater or equals to gradient of fx1 transpose x2 minus x1. Okay, and here by the mean value theorem, you know that this term is equals to fx2 minus fx1. Okay, so you can say that by equation A, and suppose this is equation B, so from A and B we get this result. So in place of that you can write fx2 minus fx1, and that is greater or equals to gradient of fx1 transpose x2 minus x1. Okay, and you know that this condition holds. This condition holds when f is convex. Okay, so this is n, it's convex. So this means if this condition holds, then you have proved that your function f is convex. Okay, so okay. So now we take the last theorem, and that theorem says that a twice differentiable function. So next page we take the twice differentiable function, and there is a concept of Hessian. Okay, so next page. Twice differentiable bonus functions. So theorem is, if f is a twice differentiable function, on an open convex set, in Rn, then f is convex on that set C if and only if the Hessian matrix Cartesian matrix, and that matrix at any x point, so we take any x bar point, okay, is positive semi-definite. Okay, you have already checked that theorem is correct, and you have already solved some problem which is depend on that, and you take the Hessian matrix and check that that matrix is positive semi-definite. Okay. So therefore each x bar, which is the Cornish combination of any point, okay, that belongs to that set C. So the proof, so the proof is let us assume that your function is twice differentiable and Cornish function, and you have to prove that this is a positive semi-definite Hessian matrix. And then the converse part, if you take this Hessian matrix is positive semi-definite, then you prove that that function is convex. Okay, so let f be convex on set C, and let us assume that any point that is x bar that belongs to that convex set C. So we are then so that for each x that belongs to Rn, so this Hessian matrix is positive definite. This means h of x bar x, this is greater or equal to 0. Okay, you have to prove that this for any x that belongs to Rn, x transpose hx bar x is also greater or equal to 0. This means your matrix is positive semi-definite. Okay, so since C is an open convex set, so there exists uh, any theta, there exists a theta uh, such that for any x which belongs to Rn, that x bar plus theta of x is also belonging to that set C. Okay. So this means by convex function theorem, we have this functional value at any point which belongs to C. You take this function value, and that function value is always greater or equals to this point and theta of gradient of fx bar transpose at x. Okay, so here your function is twice differentiable function, twice differentiable. So if we use the Taylor's theorem, second order, so this equals to f of x bar plus theta of gradient at x bar transpose x plus theta square by 2 x transpose hx bar x, and there are more terms. Okay, so you can write down this fx bar plus theta x minus of fx bar, this minus theta gradient of fx bar transpose x. So that equals to, if we, this term is goes to left hand side, this equals to 1 by 2 theta square x transpose hx bar. Okay, and here this term is basically, this is the square term and that is also the square term. So this is always greater or equals to 0. Okay, for all x which belongs to Rn. Okay, so here you can write your hx is basically, because this theta is greater than 0 and that term is greater equals to 0, so this hx is positive semi-definite for all x that belongs to comma set C. Okay, so now if we take that this matrix is your Hessian matrix is positive semi-definite for each point in C, and then you have to prove that your function f is convex. Okay, so now in next page we take the converse part. The next page, conversely, suppose that the Hessian matrix is positive semi-definite for each point in C. Okay, so now by Taylor's theorem, we write fx2, or this fx2 can be written as fx1 plus x2 minus x1 in this manner. Okay, so this fx2 is write down that term. So x1 plus this term and that expansion of this around this fx1, so this becomes fx1 plus gradient of this fx1 transpose x2 minus x1 plus this is twice differentiable, so we take only second order. This becomes x2 minus x1 transpose h of x1, and that is x2 minus x1. Okay, so since your x1 is belongs to C, and by addition and by this hx1 is positive semi-definite for any x belongs to C. So we get this fx2 minus fx1, this term is equals to gradient of fx1 transpose x2 minus x1 plus half x2 minus x1, this h of x1 x2 minus x1. Okay, and you know that this matrix is so positive semi-definite. This term is plus sign. If you're removing that term, so this term is less than that term. Okay, so this implies this fx2 minus fx1. This term is greater than, because we this equals to that term and we removing that term, this positive term. So this is less than. gradient of fx1 transpose x2 minus x1. Okay, so you can say here directly by the previous theorem, your f is convex on C. Okay, okay. So now there is another theorem which is very parallel to this theorem, and that theorem is for strictly convex. Okay, so here next page we quickly write that theorem and say that the converse part is not true for strictly convex function. Okay, the next page, let f be twice differentiable function on an open convex set in Rn, then f is strictly convex on C if the Hessian matrix, that is H is positive definite. Okay, so this part is correct, positive definite, but converse is not. Okay, for each x that is belonging to convex set C. Okay, that is you say that or you say that for each, mathematically you say that if x belongs to C, so y transpose hx of y is strictly greater than 0 for all y that belongs to Rn. Okay, so you say mathematically this thing for any x, for each x that belongs to C, the Hessian of that at that point, and you take any y belongs to Rn, this is greater than 0, this is strictly greater than 0. Okay, for strictly convex function. Okay, this function on this is a different function, and the function is strictly convex when this satisfies that. But the converse is not true. Okay, but the converse is not true. Why this converse is not true? Because okay, so okay, so we take a counter example. So now the proof, so we quickly write in only 2 minutes. So if hx is positive definite for all x that belongs to C, then from our formula or our theorem, we find this fx2 minus fx1 is strictly greater than gradient of fx1 transpose x2 minus x1 for any x1, x2 which belongs to convex set C, and here of course these two are not equal, these two are different points. Okay, so you say that your f is strictly convex. Okay, the first part is very clear, but the second part, to see the converse, see that the converse is not true. The converse is not true. You take counterexample and consider a function consider any function. Suppose we take any even order function x power 4, and where x belongs to simple real value function r1. Okay, so here f is strictly convex on r1, but if we take the Hessian means the second derivative, so this is becomes 12 of x square. Okay, and this value is, of course, for any x which is lies between minus infinity to, if it's put in 0 and here plus sign, that is always positive one. This is always strictly greater than 0. But when take this x belongs to r1, this means this x is also take the value of 0 here. For x equals to 0, this value is 0. Okay, so this is 0 at x equals to 0. So this means this value is not strictly greater than 0. Okay, this value is greater or equals to 0 when x belongs to r1. So this is not strictly signed here. So this means you say that hence is not positive definite. Hence hx is not positive definite, because here hx is the positive semi-definite. So that's why the converse part is not true for strictly convex function. Okay, तो आज हम इतना ही करते हैं और नेक्स्ट क्लास हमारी कल है। तो कल हम कोशिश करेंगे कि और 2 क्लास है तो उसमें हम तो आपको छोटा सा इंटरवल दे देंगे, उसमें हम क्लास करेंगे और कल देखते हैं क्या है। ओके, कल आज तो मैं सिम्स डिपार्टमेंट में क्लास लिया तो नेट का कोई इशू नहीं है, बट कल मैं घर से लूँगा। आप देखते हैं कि इंटरनेट कनेक्टिविटी क्या रहती है। ओके, और अगर गड़बड़ होगी तो फिर मैं कुछ और भी सोचूंगा। तो कल मैं घर से ही लूँगा।
सर सर थ्योरी के मार्क्स कब मिलेंगे?
डिफरेंशियल इक्वेशंस के ना?
यस सर।
मिल जाएंगे सब मिल जाएंगे, सारे मार्क्स मिल जाएंगे। अभी यूनिवर्सिटी आज से ओपन हुई है, अभी स्टाफ 50% पे भी आपके आना स्टार्ट किए हैं, तो मोस्ट प्रॉब्ली मंडे से वो आना स्टार्ट करेंगे। तो एक बार मैं पूछवा लूँगा वहाँ पे कि क्या इशू है, मार्क्स क्यों नहीं जा रहे हैं। तो मान के चलिए कि इस मंथ के लास्ट तक हो जाएंगे, प्रॉब्लम रिजॉल्व हो जाएंगे। थोड़ी लॉकडाउन के कारण और बाकी चीज़ें थोड़ी सी रुक गई थी यूनिवर्सिटी में, तो उसको हम करा लेंगे। ये मेरी जिम्मेदारी है, मैं आपके इस मई एंड तक मैं करा दूंगा किसी भी तरह। ठीक है, मंडे से हमें लगता है सारे स्टाफ आने शुरू होंगे धीरे धीरे।